Good morning, everyone, and thank you so much for joining us on our final day of press conferences here at the 244th meeting of the American Astronomical Society. It is Wednesday, June 12th, 2024, here in Madison, Wisconsin, and we're going to be hearing about more stars and distant worlds. I'm Kerry Hensley. I'm the Deputy AAS Press Officer. Also in the room today are Susanna Kohler, AAS Press Officer, and Benjamin Casses, the AAS Media Fellow. I want you to take a moment to please silence your cell phone or anything else that might make noise during the briefing. All of the press releases, slides, and recording related to yesterday's press conference are available on the press kit. You can also find any press releases on the AAS Press Twitter account, as well as in the Press-Conferences Slack channel for this meeting. So a brief overview of how this works in case this is your first AAS press conference. I'm going to give a brief introduction of our speakers. We'll then hear from them in the order in which they're sitting. We also have one virtual presenter joining us today, and then we will have Q&A from both people sitting here in the room as well as anyone who's watching at home on Zoom. So we won't break for Q&A in between the presenters, so please hold your questions till the end. And for our offsite journalists, you can use the Zoom Q&A feature to queue up your questions. So this morning, we're going to be hearing about more stars and distant worlds, so a pretty broad category for the first of our two press conferences today. Our first speaker will be Mary Barsony, speaking on twin jets and twin disks, JWST and ALMA discoveries in a young multiple system. Then we'll hear from Breanna Binder joining us remotely from the California State Polytechnic University, Pomona, speaking on X-ray emission of nearby low mass and sun-like stars with directly imageable habitable zones. Then we'll hear from Roman Gerasimov from University of Notre Dame, speaking on the first observations of brown dwarfs and globular clusters with JWST. And finally, we'll hear from Juliette Becker from the University of Wisconsin-Madison, speaking on the fate of oceans, survival of oceans on habitable planets orbiting white dwarfs. So with that, Mary, you want to take it away?
Thank you. Good morning, everyone. Do I have this share here? Can I? Okay. It's okay. It's a little bit of a, I can't.
Ah, sure, we can move that.
Just a second.
Let's see, can I close that?
You want to try the mouse?
Oh, no, let me. There you go.
Thank you. Thank you. All right. So it's a real treat to share with you some jaw-dropping discoveries we made with the JWST and ALMA, and especially by combining results from the two in the young multiple system that my JPL colleague Mike Ressler and I have been studying for decades. At left, you see a beautiful mid-infrared image of the nearby row of star-forming cloud core acquired by the Spitzer Space Telescope, the predecessor to JWST, revealing hundreds of emitted young stars. The subject of our work is the red object called WL20, which is expanded into the artist's conception at right. The work I will be describing is the subject of a paper that was submitted to the Astrophysical Journal along with my co-authors listed here. Please contact me at this email for preprints of the paper in advance of publication and for further information. This slide emphasizes the dramatic difference between optical and mid-infrared observations to drive home the point of why observing in the mid-infrared is so crucial to study star formation. The Rho-Oph star-forming region is among the closest to Earth at a distance of 400 light years. It is a favorite of amateur astrophotographers. At left, you see a colorful picture of the Rho-Oph cloud core at optical wavelengths, about 0.5 to 0.7 microns. By eye, Rho-Oph is the blackest region seen against the Milky Way due to obscuration by interstellar dust. At right, you see the same region of sky imaged at mid-infrared wavelengths ranging from 3.6 to 8 microns. The mid-infrared image reveals many fuzzy reddish and pinkish objects. These are young stars forming in the cloud core. We can see these mid-infrared light for two reasons. Light at mid-infrared penetrates the intervening dust further than optical light can, and these objects radiate most of their energy at these wavelengths. The small white circle in the mid-infrared image is the subject of our study. Here is the expanded view of the small red source encircled in white in the previous slide, also known as WL20. That single source turns out to be a young triple system. Unlike the sun, many stars are found in binary or higher order multiple systems. You might wonder, so what? So we have a young triple system. What's so special about it that it merits further study? The answer has to do with the peculiarity of the third southernmost component of the system. It is the faintest of the three at the shortest infrared wavelengths, and it becomes brighter at the longest mid-infrared wavelengths. In addition, it's much more dust obscured than its northern neighbors. We estimated the age of the northern sources to be 2 to 2.5 million years. However, the peculiar brightness behavior of the southern source at different wavelengths is consistent with the appearance of protostars that are less than 1 million years old. How could this be? So we took a look with the James Webb Space Telescope's mid-infrared instrument and found that the southern source is actually comprised of two. In the next slide, we focus on the region outlined by the white dashed lines in the new JWST image at the bottom in this slide. Here is the appearance of the outlined region from the last slide at 3 specific wavelengths at which ionized iron, nickel, and argon radiate. White arrows point to each of the jets to guide your eye. We were absolutely stunned when we first saw these images of the ionized twin jets in 9 different mid-infrared spectral lines emanating from each of the 2 sources which were previously thought to be one. The jets must be extremely hot since they are composed of ions which are individual atoms with an electron stripped away. Only the mid-infrared instrument known as MIRI in its medium resolution spectroscopy mode was capable of making these discoveries. It delivers images at hundreds of mid-infrared wavelengths of the same object, enabling the identification of gases of different compositions since each element radiates at its own unique set of wavelengths. Millimeter waves can also penetrate interstellar dust, although they are sensitive to different features than an infrared observatory. The cold gas and dust disks surrounding the quadruple system in Roof emit millimeter waves that can also penetrate the surrounding dust cloud. The Atacama Large Millimeter Submillimeter Array, or ALMA, is a collection of over 60 radio telescopes in Chile working as one, and it imaged this system. Here is what it found. ALMA detected the 2 northern sources, each with disks with sizes that would extend out to just beyond Saturn's orbit where they located in our solar system. The ALMA structure associated with the southern source, however, could easily have been interpreted as a single large edge-on disk with a central gap if we did not have the JWST discoveries of a new twin or of the twin parallel ionized jets in the system. Let's combine JWST's and ALMA's discoveries so far in this young multiple system. In the 4 right panels, going clockwise from top left, we see the ALMA disks image. In the remaining 3, we see the jet images in ionized iron, argon, and nickel discovered with the mid-infrared medium resolution spectrometer aboard JWST. The composite image in the single left panel combines all of the ALMA and JWST images into a single picture featuring the twin disks and the twin ionized jets discovered by both instruments together. But that's not the end of the story. To our amazement, JWST also revealed an hourglass-shaped biconical structure in molecular hydrogen heated to 2400 Fahrenheit, which you see in the left panel. The apex or narrowest part of this molecular hydrogen cone is centered on the twin sources with the cone's symmetry axis parallel to the twin jets. Molecular hydrogen does not emit at the wavelengths to which ALMA is sensitive, but the next most abundant interstellar molecule, carbon monoxide, does. ALMA is sensitive to much colder gas, say at temperatures of minus 460 Fahrenheit, which is about the ambient temperature of the cold interstellar gas out of which the young stars form. Mapping the distribution of the cold cloud gas surrounding the system, we find an almost perfect anti-correlation between the hot molecular hydrogen and the cold carbon monoxide. Our combined JWST and ALMA discoveries reveal twin parallel ionized jets and twin extended dusty disks never previously seen in this young quadruple system in the well-studied nearby row of star-forming cloud. The illustration at right combines the further JWST and ALMA discoveries of the hot biconical molecular hydrogen wind, depicted in magenta, and the nearly complete destruction of the primordial gas clouds out of which the system originally formed, found by ALMA, represented as the billowing orangish clouds to either side. To find out more about this research, how stars transition from youth into adulthood during the phase when planets are forming in their disks, contact me at this email address. And you're welcome to attend the scientific talk on this work, which I'll be presenting in person tomorrow at 10 a.m. in the Hall of Ideas 1 during oral session 413. Thank you. Exit out.
Yeah.
Thanks.
Okay, we're going to go ahead and switch to our virtual presenter here. So Breanna, if you want to go ahead and share your slides.
All right.
All right, I think we're good.
All right. Well, thank you so much for giving me this option. I'm so sorry I can't be there with you all in person. But I am going to talk about a new paper that we just recently submitted. So these are my collaborators down here. If you'd like to get into contact with me, email is the best way. And in this study, we looked at X-ray emission from nearby sunlight and low mass stars with directly imageable habitable zones. So what I mean by that, next generation telescopes such as the Habitable Worlds Observatory or the Extremely Large Telescope program, which is a ground-based effort, have as one of their primary goals to be able to directly image Earth-like planets in the habitable zones of their parent stars. So on the left, under the Habitable Worlds Observatory logo, you see a simulation of what our solar system might look like to HWO in the future, where we can actually directly image Earth, Venus, Saturn, Jupiter. And planets that reside in their stars' habitable zones are, of course, very interesting. And beyond just imaging them, we hope to also be able to obtain spectra of these planets so that we can study their atmospheres and hopefully find the elusive Earth 2.0. But there's a lot more to a planet being habitable than just, is it at the right distance from its star? There are a lot of other factors that go into habitability. And so in order to find these planets that we may be able to get spectra of, we need to first know what stars we should look at. There are lots of stars nearby, and we want to know which ones are going to be the best ones that are most likely to host Earth 2.0. And one factor that can affect a planet's ability to retain an Earth-like atmosphere is the high energy environment in which that planet resides. So we can make this question a little bit more specific here for the purpose of our study and say what habitable zone planets reside in high energy environments like the Earth. So X-rays and extreme UV emission can ablate planetary atmospheres. If you have too much of it, it can irradiate and sterilize surfaces. And so, we know that the Earth was fine. The sun emits X-rays, and it's always emitted X-rays. And the Earth, for the vast majority of its history, has been inhabited. So we want to know which nearby stars have these high energy environments similar to that the Earth evolved in. So we made a preliminary list of 229 nearby FGKM stars. So these are stars that are more or less like the sun, a little bit hotter, some that are cooler. And we see the spatial distribution of this 229 stellar sample on the left here. So the sun is at the middle. The concentric white circles represent 5 parsecs, 10 parsecs, and 15 parsecs in distance, so you can get a little bit of sense of spatial scale. The stars are color-coded by spectral type, so those light yellow points are F stars, ranging all the way down to the red points, which are the M stars. And we searched the Chandra and XMM Newton archives for stars that had been contained within the field of view of at least one X-ray image. And so stars that have been imaged with one of these X-ray telescopes have the blue halos around them in that rotating figure. We found that 57 stellar systems were contained within at least one X-ray observation with Chandra or XMM Newton. The total exposure time of these observations totals up to more than 34 days, so more than a month of continuous observing. And an additional 19 stellar systems have been observed by the Swift X-ray telescope. And so putting these numbers together, I just want to emphasize that only about a third of potential target stars for direct imaging studies have been observed with a modern X-ray facility, and we can actually characterize their high energy environments. So from these observations, we were able to extract light curves and model spectra, and the big results of our study comes down to this plot. It gets kind of messy, so I want to walk you through exactly what this plot is showing, and then I'll put up a summary table of the results that's a little bit easier to read. But what this plot is showing is along the horizontal axis is a ratio, the log of a ratio between the X-ray luminosity that a star produces and its broad optical luminosity. So we call that the log LX L-Bol ratio. And on the vertical axis is the percent of time that a star spends below a certain LX L-Bol ratio. So on this plot, if you have a star that is perfectly not variable in X-rays, it should look like a straight vertical line, meaning the star is just constantly emitting at some X-ray luminosity and it doesn't change at all. If you have a star that is changing a lot, for example, through giant flaring events, you should see a line that has a much more extended horizontal extent. All right, so for some context, we wanted to know which of these stars are producing solar-like environments. So let's put the sun on here to give us some extra context. This is the range of this diagram that is occupied by the modern day sun. So the sun is not a perfectly straight line on this plot, but it also does not have a super extended horizontal component to it. So this is where the modern sun resides. In the past, about 4 billion years ago, the sun was fainter than it is today in the optical, but we think it was a little bit brighter in the X-rays. So if we were to go back in time, about 4 billion years ago, the early sun would occupy this area on the diagram. And if you go into the region of this diagram to the left of the modern sun, these are environments that are less hostile than the environments in which Earth evolved. And if you go to the right, you're in more hostile high energy environments than the Earth evolved. This is a fairly conservative estimate that we are making here. It is possible that you could have an Earth-like planet orbiting a star that's in a slightly more hostile high energy environment than what the Earth evolved in. And the planet would still be able to retain its atmosphere and be okay, but we don't know exactly where that cutoff line is. Like, we don't know exactly how much X-rays is too much X-rays. It depends on a lot of other factors about the planet. So we're going to go with this scheme, and the lines that I'm going to throw up on here are also color-coded, just like in that rotating diagram of the distribution of stars, where the lighter yellow lines are representing the X-ray emission from stars that are hotter than the sun. The orangish colors are sunlight stars, and red get to cooler stars than the sun. And so this is what the final, our big major takeaway plot looks like. You can see as you go to the right on this diagram, those more hostile environments, the lines become more dominated by dark red, meaning M dwarfs, stars that are smaller and cooler than the sun, tend to produce significantly more X-ray radiation and flare a lot more than the sun. And because this plot is a bit of a mess, like I said, each one of these lines on here represents an individual star from our sample. We also tabulated the stars that lie in those gray and blue solar regions and stars that live to the left on this diagram that are less hostile than the Earth. And so this table here on the right that I'm showing lists the stars that have some kind of solar-like LX-Lbel ratio. So this is the list of stars where if they had Earth-like planets in their habitable zones, that we expect those planets were residing in a high-energy environment that's similar to the ones that Earth has evolved in. The very rightmost column in this table says HWO tier. This is a system of classifying stars that are potential targets for the Habitable Worlds Observatory for their direct imaging surveys. Stars that have a tier A are very, very good candidates that are highly likely to be observed with HWO. And the B and C tier stars are stars that might be good targets, but we don't have enough information about them yet to know if they really are the ideal targets to be investing valuable HWO time on. And so we're hoping that this study can kind of help to make that decision about which B and C tier stars are maybe worth looking at because they have high energy environments that are conducive to Earth-like planets evolving, and stars that didn't make the list, maybe those would be tougher environments for Earth-like planets to maintain atmospheres. So that is where I will conclude. This work was submitted. The paper describing this was submitted to AppJ earlier this week. And if you would like to get in contact with me, you can reach me at the email address on the screen. Thank you.
Good morning, everybody. My name is Roman Gerasimov. I am from University of Notre Dame, and I study, if I could go to the next slide, sorry. I can't go to the next slide. Okay, now I can. Awesome. Sorry about that. I study galactic archaeology, which means that I get paid for trying to figure out where the periodic table came from. I am trying to understand the process that took the universe from the primordial soup of hydrogen and helium to this incredibly chemically diverse environment that can sustain complicated objects like astronomers. And in order to do that, I look at very old stars because their chemical composition would capture the very first steps of this process. And if you are looking for very old stars, then you need to look at globular clusters within our galaxy. Here's a picture of one of them. There are about 150 of them in the Milky Way. And some of those objects are older than 13 billion years, which means that they host some of the first stars to emerge after the Big Bang. In particular, for galactic archaeology purposes, I would like to know what their chemical composition is, and I would like to know how old they are so that I could figure out where that chemical composition belongs in the grand cosmic timescale. And it turns out that to answer both of these questions, you can look at a very special type of an astronomical object within those globular clusters that is called a brown dwarf. Brown dwarfs are similar to stars, except they are much lighter. Their masses are below 8% of the mass of the sun. And because of that, they are incapable of sustaining hydrogen fusion in their cores. That means that unlike stars that have approximately the same brightness throughout their lifetimes, brown dwarfs cool down over time and they get fainter as they age. And this is a good thing, as that means that by looking at a brown dwarf and by measuring its temperature, you can figure out how old it is. So you can use it as a sort of galactic chronometer, and if you find one of these or multiple of these in a globular cluster, you may be able to estimate its age. I have to emphasize that the cooling behavior of brown dwarfs is also very sensitive to their chemistry, which means that you can use them as chemical tracers and get the compositions of globular clusters from these objects as well. The problem is that globular clusters are very old, which means that brown dwarfs in globular clusters are going to be very old, which means that they would have cooled down to very low temperatures and they would be very faint. They would be so faint that until 3 years ago, it was impossible to observe them at all. What changed 3 years ago is we got James Webb Space Telescope that is so well suited to this type of science that not only is it possible to observe these objects now, it is actually, I would say, not that difficult to do. We pointed JW at this globular cluster. This is NGC 6397. Specifically, we looked at this patch of that cluster using an instrument called NearCam on board of James Webb. And we took an exposure, and this is what a part of that field looks like. And you can spend all day counting galaxies in this field, but what we were trying to figure out is which of these objects that you see here are legitimate members of the cluster, and which of these objects simply happen to be in the same part of the sky and are completely unrelated. And the way you can do that is by looking at their velocities. So if you think of a globular cluster as a bunch of member stars, those are indicated here with red. And there's also going to be a bunch of imposters. Those are non-members that just happen to be in the same part of the sky. If you look at their velocities, then all of the members are going to be moving in roughly the same direction because they share the same origin, whilst all of the imposters are going to have random velocities. And this is how you can tell them apart. So what you really want to do is observe the same patch in the globular cluster not once but twice, so you can see how things change and what kind of velocities these objects have. So the reason why we picked that specific patch of the globular cluster is because about 20 years ago, it was observed with Hubble Space Telescope over the course of 120 orbits. It is the deepest Hubble exposure of any globular cluster. And even though it is still not sensitive enough to identify brown dwarfs in it, it was good enough to figure out where these objects were, which is all we needed in order to be able to tell if they are members or not. So once you know which of those objects are members, you need to measure their temperatures, because this is how you can tell if you're looking at a cold brown dwarf or a comparatively warm star. In order to do that, you would have to compare the properties of these objects to theoretical models. And as it turned out, the chemical environments in globular clusters are so unusual that the models that we needed did not exist, and we had to create them from scratch. And this is where we had a lot of help from an undergraduate student, Efrain Alvarado, who worked with us at UC San Diego last summer. So if you're curious about the new models that we calculated for this study, if you'd like to use our models, then please check out his poster at 9 a.m. tomorrow. Finally, with those new models and with membership information, we were able to identify 3 confirmed brown dwarf members of NGC 6397. Here are their pictures, their mugshots, shown here for the very first time. We were able to measure their temperatures that vary from about 1300 to 1800 Kelvin. This seems hot by human standards, but it is much colder than any of the stars that we have ever seen. And based on those temperatures, those are most definitely brown dwarfs and not stars. We also estimated their sizes. They are all, as it turns out, smaller than planet Jupiter, which is what you would expect of a brown dwarf. So to bring everything together, we have been able to identify 3 members of the globular cluster NGC 6397. We know that they are members, and we know that they are brown dwarf members. And this is the first time that we have been able to do that, thanks to the unprecedented capabilities of JWST. Because globular clusters happen to be some of the oldest things that we know of in the universe, by proxy, those would probably also be the oldest brown dwarfs that we currently know. Now, at present, we only have 3 of these objects. In order to be able to do real statistics, we would need a significantly larger number. And the limiting factor right now is those archival Hubble data that I mentioned. Only the absolute brightest brown dwarfs can have their membership confirmed in this way. And in order for us to be able to discover more of these objects, we need to move away from Hubble, and we need to have both observations to be taken by JWST. So the logical next step here would be to visit this globular cluster and other nearby globular clusters with JWST again. We should be able to do that in about 3 years' time. And then I am convinced that instead of just 3 objects, we will have hundreds of these new objects. And then we'll be able to talk about estimating precise ages of globular clusters using this brand new technique, as well as measuring their chemistry at the very low end of the distribution of masses within those objects. Thank you very much.
All right. Hello, everyone. So my name is Juliette Becker, and I'm a professor at the University of Wisconsin-Madison. And today I'm going to tell you about work that I did in collaboration with my collaborators, Andrew Vanderberg at MIT and Joseph Livesey, who's a graduate student here at the University of Wisconsin-Madison. And today I'm going to tell you a story that could potentially end in habitable planets, but there's a lot of pitfalls along the way that could prevent that from happening. So what I'm going to specifically tell you about today is what happens to oceans on planets around white dwarfs. So to start with this, it might help to define exactly what a white dwarf is and how you make one. So I'm going to start by posing a question. What will happen at the end of the sun's lifetime when it runs out of hydrogen to fuse? And this is actually something that will happen to all low mass stars, not just the sun. The process that the sun will go through at this point is a very violent process. So I have here an animation from ESA that demonstrates the first phase of this. In this animation, you can see Mercury and Venus as little pinpricks in the background. Then you can see Earth as a foreground object. And what happens when the sun runs out of helium and hydrogen to fuse is it's going to expand in radius and become another object called a red giant. Red giants can be up to 100 times the radius of the sun. So as you can see in this animation, this results in the radius actually exceeding the orbital radius of the planets in our solar system. In our own solar system, many people have done simulations and determined that not only are we going to probably lose Mercury and Venus, but even the Earth itself will, at the pinnacle of this red giant phase, be destroyed. So this is not great for planets and not great for habitability, but what you're left with after this red giant phase is the super dense core of the star, which becomes a white dwarf. So white dwarfs are very unique astronomical objects. So our sun will turn into a white dwarf with about half the mass of the sun. So half of that mass will be lost to space. But this collapse process that happens after the red giant phase actually results in the white dwarf being supported by electron degeneracy pressure and being about the same size as Earth. Now, this is actually very fortuitous for those of us who want to study biosignatures and find life, because this makes white dwarfs very good targets for characterization of potentially habitable planets, if such planets could exist around white dwarfs. The reason for this is that because the white dwarf is so small in radius compared to the planet orbiting around it, then all of our methods, which rely on the contrast ratio between the size of the planet and the size of the star to get atmospheric constraints, are overly successful. So this is a great paper by Lisa Kaltenegger from 2020 showing that you could actually, if you did find a potentially habitable planet around a white dwarf, you could characterize it very well using JWST. However, there is a challenge first, which is first, we have not found these habitable planets. And secondarily, the path that a star takes to become a white dwarf is very dynamically violent. It changes the character of the system. And if we think a planet requires water to be habitable, which is currently the consensus, then these planets need to retain their water through this process of stellar evolution and retain their water while they move into habitable orbits. So this is kind of the underlying challenge for habitable planets around white dwarfs, is that this path to get from an orbit around a star like the sun into a habitable orbit around a white dwarf is very perilous. Many planets will not survive the journey, such as Mercury, Venus, and Earth in our own solar system, but even more planets that do survive the journey may not be able to keep their surface water. So there are two main challenges that I'm going to talk about today. The first one is surviving the star, this process of stellar evolution that takes a star like the sun and turns it into a white dwarf, the degenerate core remnant. So if you run simulations of what will happen to the sun in this future, you can look at the luminosity, so that's the brightness of the star as it transitions from a normal sun-like lifetime to this white dwarf phase. And notice that the y-axis here is in log space. So this spike right in the middle, which is where the red giant phase occurs, is actually 10 to 100 times brightening of the star's brightness. After the star becomes a white dwarf, then the luminosity, the brightness starts to fall off and just decrease with time. This cooling process is actually very similar to what you just heard about with brown dwarfs. So white dwarfs don't have any nuclear fusion to provide new energy. They're just cooling with time and getting dimmer and dimmer. An additional complication is that in this transition from a sun-like star to a white dwarf, the star itself is going to lose about half its mass in a very quick phase after the red giant phase. This results in the orbits of planets around that star increasing their orbital distances when this mass changes to conserve energy and angular momentum. This again results, if you put all of these pieces of physics together and compute what happens to the temperature on the planet, it results in a temperature that, while it's pretty stable for most of the star's lifetime, during this phase, the temperature spikes and then spikes again. The impact of this temperature spike is it has the potential to evaporate a planet's oceans into the planet's atmosphere, and then after that, lose those atmospheres to space using the same X-ray and ultraviolet radiation that you heard about 2 talks ago. So on the bottom here, you can see what would happen to 3 different planets with different initial orbits. So the planet at the bottom here that loses all of its ocean is one that started at 4 astronomical units, which is slightly anterior to Jupiter's orbit in our own solar system. And what you'll notice here is that for planets to keep their oceans during this phase of stellar evolution, they have to start out pretty far away from the star. Past Jupiter, even past Saturn, is more helpful for retaining these oceans. But this is actually not the final challenge to these planets. So the second challenge to maintaining these oceans on planets is that the planet, to become habitable, has to travel relatively close to the white dwarf because the habitable zone is close to the surface of the white dwarf. So the oceans have to not only survive the stellar brightening that happens during the red giant phase, they also have to survive this journey to the habitable zone. So the mechanism by which these planets are thought to move into the habitable zone around a white dwarf is called tidal migration. In tidal migration, the semi-major axis of a planet will shrink over time as energy is dissipated via tides raised on the surface of the planet. As this happens, in the third panel, you can see the amount of heat that you get on the planet as a consequence of both the tidal heating and then also the radiation that's being pumped into its atmosphere by the white dwarf itself. And on the bottom here, you can see what happens to the oceans on the planet. For this particular set of initial conditions, no ocean survives. So this planet, even if it got to the habitable zone, wouldn't have any water left at the end of this. However, you can also delay the beginning of this journey. So this journey that you're seeing here starts right after the white dwarf forms. But if you can delay that journey by 1 billion years or so, which is not long in terms of a white dwarf's lifetime, then this means that the amount of X-ray and extreme ultraviolet radiation that the white dwarf will be pumping into the planet's atmosphere will be less. And the comparison here is look at that bottom plot, which shows the amount of ocean remaining. The amount of ocean remaining, if you delay the migration, is going to be much higher. We can put these all together and we can look at one final plot that describes what happens to oceans on all of these processes put together. So on this plot, the x-axis is the final orbital distance. So how far away is the planet from the white dwarf at the very end of this perilous journey? And then on the y-axis, we have the temperature of the white dwarf at the moment the planet scatters in, or over on the other y-axis, I've converted this into an age of the white dwarf. So how long has it been since it shed its outer envelope and all that was left was that degenerate core of the white dwarf? And the colors here tell you how much ocean is remaining. Blue means you're keeping about 1 Earth ocean worth of water. So this particular planet was one that we started with 2 Earth oceans of water at the beginning of the evolution when the star was on the main sequence. And then red here means you have no ocean remaining at all. So if you look at this plot, it looks like, okay, there's a pretty good parameter space where oceans can survive, but we don't actually only care about oceans surviving. We care about oceans surviving and the planet being in the habitable zone. The habitable zone itself is going to change location as the white dwarf cools, because as the star gets cooler and cooler, for your planet to be warm enough for water to be liquid, the planet needs to be placed closer and closer to the star. So we can overlay on this plot the location of the habitable zone. And what you'll notice is that the intersection between this blue region where ocean survives and the location of the habitable zone is actually quite narrow. So the question of can oceans survive on planets around white dwarfs is technically yes, because we do have some cases where planets can survive the stellar evolution and keep their oceans even as their star evolves. But it is not an easy process. There is no guarantee that a planet will keep its oceans while it undergoes this migration process. If you want a planet to survive and keep its oceans, then it must first avoid engulfment by the star, which means it needs to be at least several times as far as, a few times as far as Earth is from the star. Next, it has to be sufficiently distant from the sun so that during the red giant phase, the oceans don't evaporate and become lost due to that brightening in the star. And then finally, the oceans also have to survive tidal migration, which means that the migration must not occur immediately when the white dwarf forms, but it must occur later in time. So the summary to this of how can oceans survive on potentially habitable planets around white dwarfs is by meeting these many criteria, a small proportion of planets could potentially have their oceans survive, but it's by no means the dominant outcome. Most planets are going to lose their oceans throughout this process. So the work that I've just presented to you today has been submitted to AAS journals, and I have here at the bottom of the slide my contact information, including my email and phone number if anyone has more questions or would like a preprint. And thank you all so much for your attention.
Oh, all right. So it's now time for our Q&A. If I can figure out how to get Zoom to cooperate. Oh, wait, no, here we go. We were just hidden over on the side there. Okay. So we'll be taking questions from people in the room as well as on Zoom. So just a reminder to please identify yourself by name and affiliation and say who your question is for. So let's start with questions here in the room.
Yambo Penn, University of Michigan. Thank you very much for the great talks. This question is for Juliette Becker. So you mentioned from the radiation from the white dwarf, the ocean is evaporated. did your team obtain any observational evidence for the water-enriched atmospheres? And did you like run any retrievals on it to get the abundance?
So that's a great question. Is this on? Okay, so that's a great question. So we're very much in a theoretical landscape right now because the only planets that we found close to the white dwarf in the habitable zone so far are actually giant planets. We have not found a single terrestrial planet. And part of that is because the transit probability is very low. The transit duration is very short because the white dwarfs are so small. So they're very hard to find. So despite the fact that these are really great targets for biosignature searches, we actually don't have any candidates yet to look at. So part of the purpose of this work is just to determine, once we find these candidates, is it worth devoting the JWST time to actually look at them? But great question. That is hopefully the future of this work.
Thank you.
Thank you for the great talks. My question's for Mary. Oh, my name's Nick. I'm from University of Oklahoma. So your target's very interesting. It's a quad system with not a compact, but a relatively compact multiple, the binary star, which are seemingly aligned together based on their angular momentum, well, their jets. So have you posited what the formation mechanisms to kind of create this compact quad multiple?
Well, the short answer is we don't know. We're still trying to understand how multiples form from the original collapsing clouds, and that's a subject of investigation. Yeah, because most systems do. In fact, the youngest systems seem to have a higher multiple fraction overall than at a few 100,000 years than they even do at a few millions of years. So there's a lot of dynamical things going on. So no, what's also very interesting about the system from that perspective is generally you expect a close binary to have truncated disks, right? And the ones that are further away to have the larger disk, and we see exact opposite. So I'm just inferring there must be an awful lot of dynamical interactions going on during the early short part of the formation, but we don't yet have an answer to your question.
Yeah. Just one more follow-up. So you got ALMA data on this. Did you get kinematics for the disk?
We do in the molecular CO 13C on C18O, these are not detected, the two smaller ones. And it's barely detected in C18O, the one around the larger dusty disk. In fact, the ratio of gas to dust is 10:1 or less in mass. So it's very depleted in gas. So no, there's not enough there to get kinematics for the two disks.
Thank you.
Thanks. This is Rick Feinberg, freelance. In follow-up to the previous questions for Dr. Barsony, it seemed at the beginning you mentioned that you had 3 sources, then you discovered you had 4. You mentioned that the 2 northern sources appeared to be 2 million years old,
Yes.
and the southern ones
Yes.
younger. So how confident are you that this is truly a 4-star multiple, or whether you've got a tight binary and 2 unrelated stars? And what is the relationship between the twin systems, parallel disks and jets, to the fact that the age is different from the northern ones?
Okay, that's a lot of questions. We know that I didn't have time, of course, in 7 minutes to tell you, but the ages are determined from near-infrared spectroscopy. We have the spectral types for the 2 northern ones, and also from the luminosities, and then we compare them with all sorts of pre-main sequence evolutionary tracks. So that's the age. And the distance between these is a few hundred astronomical units. And the general size of a core that's collapsing is much, much larger than that. It's 10,000 AU typically. So that's the basis on which we assert that they're formed from the same core. I'm sorry, what were the other questions?
Well, the question is how confident, I mean, is it truly a 4-star
Yes.
system, or is it 2 separate systems?
No, it's truly a 4-star system because once now we have that they're edge-on disks, that explains the extra extinction in the line of sight. And the fact that they have these jets still means that they can't be hugely older than a few million years. And so, in fact, what's interesting is that these are older than the protostars that people generally study with outflows. We don't see the CO outflows, which are typically the hallmarks of very young stars, and that's because the cloud material is gone. So that also is consistent with it being with the two close ones being older, because the material out of which they formed now is gone.
Hi, I'm Max Croft. I'm a grad student here at UW-Madison. I have a question for Breanna Binder. I was wondering, how are the HWO classifications determined, like the ABC?
Oh, yeah. So we took these, there's a white paper by Eric Mamajek, and they're basically determined by how easy the star is going to be for HWO to image. So like, where is the habitable zone relative to the inner working angle constraints? Is it in a binary or a higher order multiple system or not? We think that binaries are going to be tougher for potentially, you know, habitable Earth-like worlds to reside in. So if you're in a binary, you get downgraded or excluded, etc. So yeah, the exact details of how you classify stars as ABC basically has to do with how likely do we think that the star is going to have a stable habitable zone that's going to be easy for us to image. And we basically took that from that white paper.
Hi, this is Martha from the Space Telescope Science Institute. I have a question for Juliette. You mentioned that there could be a mechanism to delay migration. Can you elaborate more on that? What would be this mechanism or mechanisms?
Yeah, so that's a great question. So to start migration, there has to be an event that excites the planet into a highly eccentric orbit. And these planetary systems, at the time the star transitions into a white dwarf, they've been existing around the star for the entire main sequence stellar lifetime. But the dynamical character of the system changes significantly when their orbits expand as the star loses mass. And this can lead to the onset of chaotic instabilities that don't happen immediately, but they can take some time to occur. So an example is in the outer solar system, there's a lot of chaotic orbits. It doesn't mean necessarily they're going to go unstable immediately. There's some amount of time before that happens. In white dwarf systems, there's a lot of really great numerical simulation work by Dmitry Veres that shows that you can have these instabilities onset immediately when the white dwarf forms, or the system can just orbit, and then the chaotic instability could happen much later. So there's a lot of simulation work that backs up that this could happen at late times. The trick is the systems are chaotic, so they're very hard to actually simulate and predict. So a lot of this is kind of a statistical prediction rather than we can't point specifically to a planetary system and say this is what's going to happen to the planets. It's just kind of a statistical expectation that some of these will scatter in late.
Thank you.
Thanks.
This is Alyssa Jankowski with the University of Wisconsin-Madison, and I have a question for Juliette. We know that giant planets often have moons around them, especially seen in the solar system with Saturn and Jupiter. Would we be able to, or I guess, how would this migration affect possible liquid water on the moons of these giant planets that might be around these white dwarfs?
That is a wonderful question. So moons like the ones we see in the solar system around Jupiter and Saturn that have substantial subsurface oceans and ice layers are actually kind of the perfect object to potentially become habitable, especially since as their giant planet hosts change their orbit, it's actually hard for all of these moons to stay bound. So it's expected that these moons might be ejected during planet migration or as the orbits of these Jupiters expand. So moons are definitely a very feasible candidate for habitable planets. The work that we did in this paper focuses on Earth-like planets, but we do mention in the discussion of the paper that something people should look into next is what happens to these moons that are smaller but can actually have even more surface water than the Earth does, as we've seen in our own solar system. So like very insightful. That's definitely the next direction to go. Thank you.
Right there. Yep.
Hi, this is Kevin from Iowa. I actually had a question for Breanna. I was just curious if you could maybe comment more on the observing strategy with stars, because you mentioned in the table you showed stars with all different X-ray emission properties. Are they all optimized to have the best contrast? And if not, is there going to be some kind of trace so they could choose targets that may not be the best contrast, but better kind of stellar properties for life? Or is it better to go only for the best contrast? I'm just kind of curious you comment on that.
Yeah, so do you mean, are you talking about the optical contrasts in terms of like what HWO or ELTs could find, or are you talking about the X-ray observations?
Oh yeah, I guess my question was, I wasn't sure, in the stars you showed in the table, were they all stars that would have the habitable zone within the inner working angle that had the best contrast?
Oh, yes. So all of the stars in our preliminary list of the 229, these are all stars where most of the habitable zone is going to be accessible to either HWO or ELTs, given kind of notional architectures that we have at the moment. So these are all stars that would potentially be good targets. They have good contrast ratios. The habitable zones are at the right distance for inner working angle constraints. So we specifically selected that initial list of 229 stars to be stars that would be very good candidates for future direct imaging studies. And then of those, we were able to obtain archival X-ray imaging for 57 systems with either XMM or Chandra.
Thanks.
Go to an online question if we've got one. Great. We have just a couple more minutes.
Sure, we have many online questions. This one is for Roman. This is from our Mark Elowitz, and he wants to know, although brown dwarfs are not hot enough for their interiors to fuse hydrogen, can they burn deuterium? And if so, how does that affect their cooling curves?
Those brown dwarfs definitely can, because we are looking at pretty much the hottest brown dwarfs, highest mass brown dwarfs that you can have, as we're not sensitive enough to be able to go below the deuterium burning limit. But the effect on the evolutionary track is relatively minor compared to that of hydrogen burning.
I'll do another. This one is for Breanna. This is from Larry Krumenacker, and he of the Galactic Times newsletter. And he wants to know, do any of the A and B candidates on your list of HWO targets have any known exoplanets? And if so, are any in the habitable zone?
So roughly half the stars in our study have known exoplanets. Most of those exoplanets, though, are Jupiter type planets. There are a lot of hot Jupiters. There are a small number that have maybe Earth, kind of Earth-like masses to them. So we don't have a large sample of Earth-like planets in the habitable zones yet, but we expect that we're going to be finding a lot more once we're able to directly image these habitable zones. So the short answer is yes, there are planets, but the vast majority of them are close in Jupiter-like planets.
We're 1.5 minutes late, so we have time for one more question. Are there more online or here in the room?
Yeah, this one is from Pamela Gay of Escape Velocity Space News for Juliette. And she understands if you have not considered this, but wants to know, can you compare the statistical likelihood of a white dwarf capturing a rogue planet versus the likelihood that migration would occur on just the right time scale for just the right type of world?
Yeah, so that's a great question. In general, we kind of have rough estimates of the free-floating planet population. And the trick would be you'd have to get that free-floating planet after it was captured into the system, which happens in the outer part of the system. You then would have to undergo the same migration process that would get it in close to the habitable zone. So without actually having a calculation to back this up, I will say that it's more likely that a planet that was bound to the host star during its main sequence life will end up habitable compared to a captured one. But it is definitely that would be an even more perilous journey for the planet than what I'm talking about.
Excellent. Well, with that, let's draw our session to a close. Let's thank our speakers one more time for their excellent presentations. Thanks to you all as well for your attention during the session, as well as to the PIOs who helped to prepare press releases. We will be back here for our final press conference of this 244th meeting of the AAS this afternoon in this room at 2:15, and we'll be hearing about citizen science of the 2023 and 2024 solar eclipses. So I hope to see you then.